actually the main point that we will cover today is about linear regression. And in fact, linear regression will give you like a foundation to logistic regression, the topic that you all want to study. Because, okay, I'll put this way, if have any of you used deep learning? Has anyone? Okay, if you use deep learning, linear regression is like one neural network with one layer, and that layer is a linear layer. And logistic regression is like you add the activation function after that linear layer, and that activation function is a sigmoid function or exponential. I'm not sure if it's just that very very simple. But what we're going to learn today will have some difficult mathematics, a little bit, not that difficult, but to just give you some idea about the properties in linear regression. That's it. Today มีอยู่คนเดียวเลยนะใช่ไหมทีมอยู่มีอยู่คนเดียวมีใครอยู่ทีมเดียวกับน้องคนนี้ไหมอ๋อยังอยู่นะเนี่ยอาทิตย์ที่แล้วเขาตามตัวเมื่อวันจันทร์ตามตัวเขายังอยู่ไหมthere's nothing now we just try to find the member of the team of a team Anyway, okay, let us define some of the variables associated with the linear regression first. So generally we have x to be our input features and y hat. Y hat is our prediction of the target, and then y is our measurements or reference. And in this case, we assume that our reference can be noisy. And yes, because our reference can be noisy, there's no guarantee that whatever we learn from we cannot guarantee that the learned model will behave as if it was trained with the noiseless measurements. So what I was trying to say is that if your measurement is noisy, there's no way for you to have like a perfect estimation. But anyway, let's assume that our measurements is noisy, and that is more like a generosity. Anyway, so firstly, if you have a linear regression can be as simple as the following formulation, where you have like beta 0 as the weight, constant weight in your linear regression model, and beta 1 to be your like a multiplication term. Usually we will call this one the bias and this one as weight parameters. And bias parameters. Just a term. Just a terminology. Okay, the weight parameters and bias parameters. And if we have this as our model, so you can see it's a linear model, and this linear model is linear in our input as well as linear in our model parameters beta. So that's something to remind ourselves. Okay, if we feed in our input, and suppose we have already provide some value for beta 0 and beta 1, then we will have y hat. Y hat will be our prediction, in which we can measure the difference between our prediction versus the reference as follow. So just negate, right? And of course, if we want to find beta 1 and beta 0 that provide the lowest residual or maybe error, okay, we definitely need at least two measurements. Is that right? Because we have two unknown. But if we have only the weight parameters without the bias, then just one measurement is enough, right? But the thing is, when you train a model, you don't always just have one measurement or two measurements. You normally have like hundreds of thousands of measurements, because that is your amount of data for training. But of course, since your model is just like a linear model, a problem that you normally encounter with this linear regression is the fact that your model will tend to have high bias. And that is because it's very simple. To make your model become more complex, sometimes people will add an activation function. As I mentioned before, maybe turning this linear regression model into what we call a logistic regression, as in we add like a logistic term over y hat. Then that becomes a logistic regression. Or maybe turning this linear model into some nonlinear model. Maybe you add beta 2 to make it polynomial. That could happen as well. Anyway, these are just examples. And the thing is, once we have this linear regression model, and because the model is simple, whatever we are going to learn in today is probably about, how shall we analyze its performance. For example, we can start by calculating the residual sum square. So with that, you can start from, doing subtraction, right, of the measurements and the predictions, and you sum over all of your samples. Then you will get RSS. And with this RSS, you can use it to then define how would you solve for beta 1 and beta 2. And that will be your optimization problem. So with, I think every machine learning model that we are going to learn in this course, most of them you have to start off with formulating this optimization problem. So it's like, how would you find the model parameters inside? Okay, let me ask you this question. We get beta 1 and beta 2 from training. And that's because we will use the training data to solve this optimization problem. But what could be our what could be our hyperparameter? First, is the number of beta. Now you have beta 0, beta 1. If you have another input beta 2, then that is, 3 betas is like the number of hyperparameters you have. The type of input features could be your hyperparameters. For example, if we go back to our house price estimation regression task, it's actually, solving this linear regression model. The input feature that you choose is your hyperparameters. And in order to choose those hyperparameters, you need validation data. I just try to recap everything so you know that there are components, associated with your problems. There are some components that use in training, some components that use in your validation. That's it. Okay. And in fact, as I mentioned before, yes, we can further extend this linear regression model to have, let's say, multiple model weights. Okay, and that's usually associated with your input features. Okay, in this case, that means you have n features, or you have n types of your input. Okay, I haven't defined how many how many training samples we will have, which is going to be m, number of samples. And usually we are referring to the training, because in order to obtain this beta 0, beta 1, beta 2, beta n, you have to solve that optimization problem. And the data that you use to solve this optimization problem is your training data that has m training samples. That's why you sum over m. Just know, okay? And of course, if you have m training samples, you have my and also mx. Okay? This is just recap. I believe many of you already understand this. Okay? Okay. And in fact, that linear regression can be turned into the following matrix multiplication formula. For example, if you only have like a beta 0 and beta 1, you can turn into this matrix multiplication formula where you have 1 as a column and x1, I was going to say x1 up to xm, but it's more like I shouldn't put the superscript in here, but anyway, okay. You see that? Okay, m. M is the number of samples. Just be careful with the notation. Okay. And if you have multiple beta, right, then you will have multiple input feature. And in this case, I put my notation for feature as a subscription. Just to let you know. Because we will do something about the row and column operations, but don't worry, I'll try to go slowly. Okay, and one more thing, y1, y2 up until ym, we also have x1, x2 up until xm. Sorry, the two is kind of close to one another. So in my notation, the superscript will be the number of samples, and the subscript is the number of features. Sorry, I think some of the lecture may use it differently, I guess. Yeah. And in fact, you can also turn your X into like a matrix form, right? Yeah, you can write each row as a vector. And don't forget that it's actually a vector of your feature. Just letting you know. And in many settings, usually we will ignore the bias, beta 0. We normally set it as 0, just like that. Especially if your input features has been normalized. So that means if your input features and your target doesn't have any, like elevated value as a constant elevating, we normally will just set beta 0 to 0. Normally. And therefore, our X will remain to just being like a matrix of your input features without this constant. Okay, that's it. And with that previous matrix form, you can now formulate an optimization problem using that previous matrix form as a least square problem. And now the variable that you want to optimize for is going to be the vector beta. It's the entire vector. Or I could write it like as a summation of the constant of the value of beta, like that as well. Right. And of course, with this least square problem, we know that in order to find the best possible beta, we can solve this least square solution using gradient descent method. And actually, this gradient descent method will have like a closed form formulation for your solution already because it's just a least square. You can compute the gradient, equate that by 0, and then you will have that your solution for beta will be the following, as the following formulation where you have the pseudo inverse of x, right? Multiplied with x and y. And the reason that we have to use the pseudo inverse of x is because of the fact that our x is the input feature of size, I think, okay, sorry, of size m times n, is not a square matrix. You can't just do like a normal inverse, right? Is there any problem? No problem. Is everything all right? You look pale หมายถึงว่าคุณชานชนดูซึมอาจารย์จะไม่เอ่ยชื่อหนูบ่อยๆ เพื่อตัวหนูเองไม่เป็นไรนะ Okay, just know that because we have this x that is not a square matrix, that's why we have to do pseudo inverse. That's it. And of course, when x is not a square matrix, right? We have to further analyze how many solutions are there. If it's a square matrix and the nullity is not equal to the zero set, then it has a unique solution. There's something about that thing. Yeah. So anyway, okay, it will come to the analysis of, well, can we actually obtain this beta LS? And if it can, what is the condition for it? So there are two cases where you can obtain beta LS, and there's unique solution to it. And there's some of it that has unique solution to it. Okay, firstly, if m equal to n, then this become like a square matrix, right? Your pseudo inverse is just an x inverse. So you can compute it, you can get your beta LS. It's simple. But if m is larger than n, therefore x is non-invertible, but you can compute for beta LS with a unique solution if the nullity of x transpose s equal to 0. Or on the other word, if x transpose x is invertible. Zero set, I'm sorry. And with that, you can compute this pseudo inverse using the linear algorithm dot p inverse. Yep. For this one. Sorry, this entire thing. That's it. That's all. Okay, please don't worry. It's just that. Okay. Our Math 2 EE gone for good now. Come back to the normal life. Anyway, there are some interpretation, as in, then if we have to look at this linear system in a vector space, where are they, right? Yes, of course. Since we are computing the beta LS with that gradient descent, there's one thing about the fact that your error vector y minus beta Lx, beta x, yes, has to be orthogonal to your linear combination. So that is a y vector, and this is like the error vector between y minus beta Ls. So that's it. It's like a property that came with the fact that when you use that gradient descent to solve for beta Ls, and usually the distance between, the error is the one that is the lowest. Okay, the shortest distance, right? Because it's the one that orthogonal, then it's the shortest. That's it. There are some properties that came up with the fact that if you can use this pseudo inverse, right? There are some to do with what is the property of these. If you multiply it back, like x multiply with the pseudo inverse backward, what is the property of this combination of matrix multiplication should be? So in this case, I denoted with a P matrix. We call it the orthogonal projection matrix. And this matrix will have the following properties. First, it has to be symmetric, and the square of it will remain the same. And because of that, because when we say that, okay, because this matrix, the reason that it has the following properties is because if you think about this one being the pseudo inverse of x, right? That means that it should remain identity. And because of that, you have to remember one thing. whenever you do linear regression, you have to normalize your input features to make sure that, it will have the following properties. As in, the norm should be equal to 1 because it's representing your identity matrix. So it's kind of, it's derived from the fact that if you want to use this gradient descent to solve your beta LS, after that, how to solve this beta LS, you need pseudo-inverse. And when you have pseudo-inverse, how are you going to make sure that this pseudo-inverse will still work on your data set? You have to make sure that your data set is normalized. And therefore, when you compute this pseudo-inverse with X, you will have this near identity matrix. That's the meaning. I'm sorry. That's the reason why some of you look at my face like there's something wrong. Need to normalize your input features. That's it. That's the meaning of this entire pages that looks scary. Okay, let's go. And yes, of course, there are Python implementation aside from those codes that I provide to you on your homework 1 coding session. You can try the following tools. And actually, if I remember correctly, some of these tools like SMOLS actually have like a built-in function to compute the AIC, BIC score that you just learned previously. You can use those tools to compute as well, and you can cross-check with the function that I wrote if you want to. Yeah. I think pretty much that's it for what we should know today. But the following are more like a mathematical details for your linear regression. Of course, with the fact that it's very simple, right? The model is simple. You can always further analyze them. And I think you don't need to pay too much attention into, what are these formula, what do they came from, and all of that. It's just to provide you some guideline. As in the future, if you have like a statistical model that you created, what can you do with it? That is more like an example for that. Let's go over some of them briefly. Like for example, you can compute R squared, with the linear regression, and that's pretty much just the same formulation for every model. It's about the same. But the thing is that is important is the fact that if we have already scale or normalize our input feature with our linear regression, we should be able to obtain the following properties. For example, we should be able to check that we have a zero bias or unbiased. And we should also be able to check that, and also the model is an efficient model. If our model is a linear regression, it will follow the following properties just discretely because it's just linear regression, and when we want to make sure that it works, then we have to ensure that the pseudo-inverse will have the solution, and then we could further derive the following properties, and it would follow automatically because of those assumptions. Yeah, it's just that. If you multiply the math, it will have this zero bias, and also the covariance will be close to identity, and that becomes the fact that our model is efficient. That's it. Yeah, these are just how I analyze if the model is efficient. And if you remember, it will be efficient if the feature information divided by, okay, if the multiplication of the feature information and the variance of the matrix, if the multiplication of that is equal to 1, that's it. But it's just a property. Don't worry, not go in the exam. Just letting you know that this is a property you can derive from the fact that it's a linear regression. But you can see that because our covariance is like the sigma multiplied by x transpose x inverse, the pseudo inverse. It's possible that you may not get exactly like an identity matrix. So this is something for you to know, right? Okay. And usually, I mean, if you have a perfect data, usually, at the end of the day, you can say that your linear regression is the best linear unbiased estimator for beta. Unbiased because if your pseudo-inverse works 100%, the expectation for beta LS should equal to beta. And it's the best because it has the efficient value equal to 1, because the multiplication between that the feature information and the model covariance will be exactly 1. So that is the reason why. That is all. And also one more properties about the linear regression is the fact that sometimes people will start asking, is this linear regression has the model parameters, the weight parameters, beta? Do they have some of these model parameters equal to 0? It's like it's asking whether or not there are non-zero parameters weight. The reason that sometimes you may want to have some zero weight parameters are two things. Firstly, sometimes it's better capturing the input features that is sparse. How can your input feature become sparse? For example, if you have something like encoding label as your input features, then your input features will be sparse because you encode it with maybe value 0, 1, 2, 3, and if you turn that into one hot encoding, it becomes 0, 0, 0, 1, 0, 0, 2, 0, 1, 0, 1, 0, 0, something like that. So that becomes like a sparse value. And also, when your weight parameters are sparse, like it has some 0 value, another good thing about it is the fact that you can further reduce the model complexity. You have less computational complexity in terms of that. So yeah, there are two good things. Okay, I'll put this way. If you have 0 model parameter, okay, good. If x, if I remember correctly, I is 0, or maybe on the other word, the vector x is sparse. Which often the case if you have like a label as if it's, oh my god, ขอโทษนะคะอาจารย์ไปกินข้างล่างก็ได้ I'm sorry. Okay, 0 model, I will shorten it, param. If you have more 0 model param, the first thing that is good is the fact that it could well encode sparse input feature. Okay. Especially those input features that has been, like transformed from the label. Like if you remember the house price regression, sometimes you may have like whether or not, like input feature like whether or not this house have air condition. So you input is yes or no. In that case, when your beta is like going 0 and 1, it actually can better capture your input features like that. Like label. I'll just call it label input feature. The second reason for it to be good is the fact that it's good for enhancing model complexity, or maybe complexity, or maybe just low runtime, because your computer doesn't need to compute those zero coefficient. So that's the reason why it's good. Okay, and for that, because we have to analyze, whether or not there are chances where our model parameters going to have zero value. Sometimes we do what we call the hypothesis testing. Okay. Is it better? Okay, I'll just capture it for the time being. พร้อมยัง? If you are ready, just nod twice. Ready? Okay. We can do the hypothesis testing, and the way we do it is simply, let's say, firstly we set up our hypothesis. That is what we call a null hypothesis. I believe that if you take some of the course in year 2, there was a course about hypothesis testing already, right? Okay. If you set up the null hypothesis to be that your beta, some of your beta are having zero value. Let's say beta I have zero value. And then you could say, okay, what is the chance for that beta to have zero value, right? After that, you start to say, okay, so let's say if you say that there's 90 something chance, then that means there are the rest about 10% that is going to be non-zero. And with that 10%, if you assume that the distribution is Gaussian, then you can find what is the value for alpha, or maybe what is the value of your maybe your parameters, so not parameters, of your parameters that, if it's exceeding this bound, it will be non-zero, or if it's within this bound, it will become zero. And after that, all you have to do is then compute the average of your model parameters. After that, you find, the normalized. The reason that you have to compute this is because it's more like you will find like whether or not this value of your beta is falling within the range of your hypothesis, null hypothesis testing. Okay, I'm sorry that I go briefly, but you can look at the detail about the hypothesis testing in the appendix. I already provided. It's not a lot. It's more like to recap what you should do, and that's it for today. จบแล้ว The reason that I don't want to go too deep is because firstly I haven't reviewed myself for this topic, but the reason for knowing hypothesis testing is more about the fact that we want some of our model parameters to have zero value, but that's it. It's not like requiring you to do all this hypothesis testing. maybe one thing that you have to remember after this course is to know that, you know, the linear regression, if you well scaled up your data, this is the most important line from this lecture, is like, then your this square solution will be the best linear unbiased estimator for beta. That is the most important things about the lecture today. And just go back to recap about, you know, like how is the bias calculated. I think I will often ask this question because if you remember the formulation for your bias, right, is the negate between expectation of your estimated model parameters versus your ground truth. So that is like the exact value to tell how far is your model from the ideal situation. So bias is very important. And do aware of the fact that when we talk about bias here, this beta is actually the ground truth ideal beta. But in general, we don't know what is the ideal model parameters. So, but this is more like, yeah, if we can achieve that, then you can do this. That's why it's important. Okay, that's it. You can now go back home. All the lectures are recorded, so please don't worry. You can look at it again.